Okay, so this is a continuation of the chymotrypsin serine protease mechanism, and where we left off last time, we had explained how we got to the acyl enzyme intermediate. This is a covalent attachment of serine 195 with the carbonyl carbon that used to be part of this peptide linkage connecting two amino acid residues. So to continue this reaction, we allow the free amino group to leave the active site. It's probably going to pick up another proton along the way and become positively charged. And that will allow the entry of the next substrate, which is water, into the active site. And that brings us to the second phase of the chymotrypsin reaction. We can draw what this looks like. We still have the carbonyl carbon covalently attached to serine 195. We have histidine 57, catalytic base residue, close proximity. And now we have the water molecule. At the active site. Now, similar to the first step of the hydrolysis reaction in phase 1, drawn previously, this histidine 57 is going to act as a catalytic base. It's going to take this proton, and now the electrons are going to sit on this oxygen to create a very strong nucleophile. So base catalysis, and now we have a very good nucleophile, this hydroxide ion, right next to the electrophilic center. And we can draw in histidine 57 in its protonated form. Positive charge. Okay, so just like last time, but this time hydroxide ion is the nucleophile, and it's going to attack at the electrophilic center, and we're going to form a tetrahedral carbon, the tetrahedral transition state. And in this geometry, the tetrahedral transition state, we realize more favorable interaction with these peptide moieties provided as what is called the oxyanion hole. And they are stabilizing the negative charge that's accumulating as we go to the transition state. This situation now is, while it's stabilized by the oxyanion hole, it's still relatively unstable, and it's going to collapse. And it has two choices. When these electrons come back to form a double bond with the carbon, we can either have the hydroxide be the leaving group, in which case we just end up back to where we started. But if we go in the forward direction, then these electrons are going to go back to the oxygen on serine 195. So serine 195 will act as the leaving group, and this is facilitated by the close proximity of the general acid catalyst provided now by histidine 57. So if it resolves in this direction, we get our free carboxylic acid. This is the other end of the polypeptide after breaking the peptide linkage, and we've regenerated serine 195. And histidine 57 is back in its deprotonated form. So in other words, it can act again as a catalytic base. So once this leaves the active site and is replaced by a new peptide bond, we're ready to start the whole reaction cycle over again. So in both phase 1 and phase 2, we're talking about generation of a strong, the base catalyst, histone 57, works to generate a strong nucleophile, converting water into hydroxide ion. Nucleophilic attack at the electrophilic center generates a transition state with tetrahedral geometry, and this is stabilized by oxyanion hole, which means the close proximity of two NH groups provided by peptide linkages as part of the enzyme that stabilize the accumulation of this negative charge. And then finally, this tetrahedral transition state intermediate is resolved, and there's a leaving group that's promoted through acid catalysis provided by histone 57. And that is the end of phase 2, and we've completed the reaction mechanism for chymotrypsin.